Hi everyone, today I'm going to explain about design of the space probe. Let's see how this model represents different scan of the 1:1 ratio of the vessel. So this is my first attempt of layer slicing in acrylic. You can see the internal but not quite. And then this one is the shell attempt and will be used as PLA base for plaster compound magnesium caster. For a space probe, the cell is completely separated from the internal metal structure. Why I choose magnesium? Because it's light and ultimately not magnetic. And this is the dissected print of the plastic model. Let's see per section. As you know from my shared Dropbox, this vessel is basically used my advanced propulsion system that can move both retrograde and prograde thrust vectoring without changing direction front back. Yet for the left and right movement, it needs to do an axial vectoring of the moment. Basically, advanced propulsion system is working through superconductor magnet. This magnet is not a permanent magnet unlike neodymium ones. This is a superconductors, could be controlled and can be switched on and off. So in order to move forward, prograde, basically it manipulates its center of mass, center of gravity by the momentum of magnetic force. It sequentially switched from the superconductors. So it is sequential, and this switching is happened for its prototype at 20,000 cycles per second or 20 kilohertz. Further development will improve maybe gigahertz in frequency. So let's see from the bottom up first. As you know, this model features a camera payload that can record live high quality footage of the descent. You can see right here. So the camera needs to be directed downward in order to have the view of the Earth below and not the empty sky above. So the flight will be retrograde ascent from Earth 90 degrees straight, and the computer chip inside will navigate and the sensor keep the vessel straight. The layers in this video, this is the first section. You see right here is the cooling module. You can see how these channels are designed very tightly. Let me get focus here. Very tightly. You can see how these channels are designed to supply liquid nitrogen to the superconductors between the metal suspension and magnesium outer body. It's filled in this area completely with argon gas. As you can see the channel right here. The core of this cooling module is solid helium. The core of this cooling module is solid helium, where the center of the channel, which is called the seats, the outer core is filled with liquid helium, and then one that directly contact with the superconductor are liquid nitrogen. The purpose of this layering is to keep the thermal cycle balance, and also it's equipped with Peltier transistor in the structure between magnesium and the internal metal, to make sure the hottest part of the body equalize with the coolest part of the body right here and in the shadow of the sun. This acts much like climate control. Now superconductor magnets, as you can see above, are extremely dependent on the cool temperature, and its power consumption is very low at the lowest temp. Yet it rates significantly as its temps getting hotter. This model is equipped with 6 core and 288 threads, so 48 threads per each core. The threads are useful for thrust vectoring, so for example the vehicle needs to go in another way, it needs to gather momentum from the rear side to this side over here to steer the center of mass, creating an arc in vector resultant force. Let's stack the module first. Now after these superconductor modules, on top of it is the interchange module. This module with after the cores, this is the interchange module. The interchange module is to separate propulsion module with the power delivery, the control and the payload. This interchange module contains channel direct coolant the liquid nitrogen back to the cooling module and to have it stamped down there. Stack it first. Let's put it the other way. Okay, let's see. After the interchange module, this is the battery module. You can see the battery, and this is what we call the interchange module. We could see battery module. This is regular polymer battery, or at least regular one. After the interchange and battery, this is what I call AP-LMGS. It's manufactured lithographically because it will not use actual mechanics that moves and create torque, but rather it will use like a turbulent switch with just like a clockwork. These are regular polymer batteries. Now after that, this is the control module. It consists of gyroscope and several CPU, or not CPU, it's digital gyro along the accelerometer. For the chips, I use some daughter boards rather than a motherboard stacked together along this circle around this side in order to fit this space right here. The storage is 10 terabytes SSD and RAID mode for redundancy. The board captured footage via the HDMI and to the APS sensor right here. The camera payload has fixed lens with 360 fisheye at the very last. The caveat here, this version needs a launcher. This version needs a launcher which I designed to gather momentum at the beginning for the last launch. This version needs a launcher which I designed to gather momentum at the beginning for a fast launch, otherwise it needs to preserve mode to launch in order to have an initial impulse, otherwise it's leveraging on only by a tiny bit, quite take a moment. So I think that's it. The stronger I get going.